Hello, everyone. Welcome to another episode of Q&A about science and technology for kids and others. And we're about to start. We've just started the pre-week of our annual summer program. So these events will be a little bit sparser the next few weeks, together with some that I'll be able to do in person with some folk, which is always fun. Well, let's see. I have all kinds of questions saved up here. I see one from Harry. Uh, what happens when an antimatter black hole and a normal one collide? Well, black holes are really a phenomenon of gravity. And gravity, like light, has the feature that the matter and antimatter versions are the same. So generally with particles like electrons, for example, that have things like electric charge, there's the particle, and then there's a corresponding antiparticle. It has the same mass, but the opposite charge. It's something that is a feature of kind of the well, it's a feature of kind of the structure of the way that one describes quantum mechanics, that inevitably for every particle, there must be a corresponding antiparticle, except it might be that the particle and the antiparticle are the same. There's sort of a fundamental feature of the way that quantum mechanics and the fancier version of it, quantum field theory, works, that says that you can, if you take sort of a system and you say, we can reverse space, we can kind of reflect everything in a mirror, we can take all space coordinates to minus those space coordinates, we can reverse time. That's kind of like doing, that's well, we can reverse space, we can reverse time. If we also reverse the charges of things, then the result of doing all three of those things must be the same as what we started from. And the fact that it works that way means that inevitably there are antiparticles to particles. Well, so having said that, that story of antimatter is something which shows up when one talks about things like particles. When one's talking about things like gravity, one is not usually talking about gravity in terms of particles. Gravity, one usually says, well, it's this kind of thing that's a feature of the structure of space-time. It's something which is some force that's exerted. We don't usually talk about it in terms of having particular particles involved. In the case of light, for example, we have these two different ways of thinking about light, either as an electromagnetic wave or as a stream of photons, particles. In the case of gravity, there's a sort of similar thing you can do, talking about gravity as being associated with a stream of gravitons. Nobody ever saw a graviton as such. Unlike photons, where there are all sorts of situations in which you can detect the presence of individual photons. In the case of gravity, it's far too weak a force, and one's far, far away from being able to sort of detect individual gravitons. But one feature of gravitons, if in the sort of hypothetical version of gravity as particles, is that gravitons are their own antiparticles, just like photons are their own antiparticles. Okay, so if you think about a black hole is, for the most part, we'll come to the little footnote where this isn't really right, but for the most part, it's a phenomenon of gravity. It's a place where kind of the structure of space-time has been distorted enough that, for example, light that originates inside the black hole can never escape. It's kind of it's just there's so much gravity that the velocity needed to escape from that much gravity is more than the speed of light. So even light can't escape from the black hole. So for an ordinary black hole, it's mostly a phenomenon of gravity. There really isn't a way to talk about sort of the anti-black hole. Now, there's one type of black hole. I should say that when one thinks about black holes, the main way that they're studied in kind of mathematical physics is rather mathematically. The whole idea that there might be some whole star that gets crushed and turns into a black hole, by the time you're studying the mathematics, all of that is lost. What you're doing is you're looking at these equations, the Einstein equations, and you're saying, there are certain configurations of space-time that solve the Einstein equation. Some of those configurations of space-time correspond to these things with event horizons where light can't escape and so on. Those mathematical solutions are black holes. Now, there is a black hole solution that involves charge as well as mass. And so there are black holes one can imagine that have electric charge. And so you absolutely can have a black hole with, for example, a positive electric charge. You can have a black hole with a negative electric charge. The mass of a black hole, in an ordinary way that things are set up, the mass of a black hole is always positive, but the charge of a black hole can be positive or negative. So you can sort of imagine a black hole with a positive charge and a black hole with a negative charge, and you can ask, what happens when those black holes meet? Well, good question. Generally, what happens when black holes meet is that they merge. And that's what was observed in 2015 when the first detection of gravitational waves happened. There was a pair of black holes that had been orbiting each other for a while, and they were steadily losing energy and kind of spiraling in. And eventually, they sort of hit and they merged. Took a few seconds for them to merge. And in that time, they released a huge amount of energy from merging. They released about as much energy as one would get if everything in the sun was converted to pure energy. And that black hole merger took place about a third of the way across the universe. But the gravitational radiation that came from that violent release of energy was intense enough that it could be detected on Earth. But so what basically happened is the black holes spiral in, they touch, they merge, they become a single black hole. The single black hole kind of blobs around for a while, and then it sort of settles down to just being its own single black hole. If you have a charged black hole with positive charge, a charged black hole with a negative black charge, I think pretty much the same thing would happen. You would end up with, it would be very little different from what happens with just ordinary uncharged black holes. You would end up with a black hole whose charge is the sum of the charges of the black holes that went into it. So nothing too dramatic happens. Now, there is one kind of thing where something a little bit more dramatic would happen, which is a white hole. So black holes are places where there's a kind of lots of mass that kind of collected and formed this area where there's so much mass that light can't escape. You get a black hole. And if you look at that process of things sort of collapsing down, eventually you form the black hole. You can imagine a time-reversed version of that, where you have a bunch of stuff that's contracted down, and instead of it being all crushed in, it expands outwards. And that's sort of what happened in the beginning of our universe. That's kind of, our universe is kind of a bit like a white hole, a time-reversed black hole. In the way that gravity works, the sort of ordinary version of a black hole is just gravity is always attractive. It's always pulling things in, but you can at least imagine a time-reversed version in which things are kind of spewing out, so to speak. And you can get that if you, it's a bit of a tricky thing to sort of see how this all works, but you can get that by essentially having enough energy in the thing that it forces everything to go outwards. That's kind of what happened in the Big Bang. But so you could ask the question, what happens when you have a white hole and a black hole that sort of meet? And that's a complicated story, because what can happen, probably not in our actual universe. By the way, to make a white hole really go, you have to have matter that has negative mass, which in ordinary matter always has positive mass. You can have a different electric charge, positive or negative, but as far as mass is concerned, mass is normally always positive. There's a footnote to that. In quantum mechanics and quantum field theory, you can have so-called virtual particles, which can have negative masses. That's a whole separate story. Also, there's sort of a hypothetical thing that is currently kind of a hack needed to explain observations in cosmology, which is this idea of dark energy, which is essentially negative mass matter. But if you can power a white hole by having negative mass, it's kind of like a negative mass black hole. And when you have combinations of black holes and white holes, you can do all kinds of wild things, like getting wormholes where you connect one part of the universe to another part of the universe, going from sort of the black hole to the white hole and so on. These things probably don't happen in the actual universe. They're things that are sort of mathematical possibilities, but they're probably things which are just a feature of the mathematics and not a feature of the physics of what can actually happen. In our models of physics, where we start from kind of a structure of space where there's actually an internal structure to space in ordinary kind of theories of gravity that have existed for the last 100 years or so, kind of the idea is space is just this background thing that has matter put in it and so on, and that the space can have certain kinds of curvature and so on. But in our models where sort of underneath there is this whole network of different sort of atoms of space connected together, this kind of discrete network, which only appears continuous on a large scale, the kind of scale that we are on, you can have a lot more kinds of effects. And for example, you can have things like things I was calling space tunnels, which are places where the dimensionality of space is no longer 3, and you have kind of these ways where you can get sort of from one part of space to another, kind of in some sense more efficiently than by sort of going through ordinary space. But so there are a bunch of exotic possibilities that exist in our models. Whether they actually were produced in the development of the universe, we don't know. We don't even know really a good classification of what all the kinds of exotic things that could happen are. By the way, in traditional kind of theories of gravity, traditional general relativity, it's also pretty hard to classify what all the kinds of things that can happen are. If you say that the thing has to be spherically symmetric, has to be sort of a sphere-like thing, then you can make some statements about what happens. But as soon as you go away from things like that, it becomes a much more complicated zoo, and it's really not clear what happens. Anyway, just a little bit on that. Let's see. Well, okay, another question about sort of black holes and things from Double, asking, could time dilation be used to speed up computers or computation? Well, the answer is kind of sort of yes and sort of absolutely no. It's always a difficult thing because the notions of time and space and so on are very observer dependent. We're not used to that. We kind of imagine time passes, we have a clock here, we have a clock there, it always goes at the same rate. We don't have the kind of idea that the passage of time, the rate at which time passes, might be dependent on the environment that we're in. But one thing that happens is, well, there are several things that happen. Let's explain the most basic one, which is the phenomenon of time dilation. If you're going faster, time effectively runs slower for you relative to someone who isn't going faster. That's a phenomenon that you can sort of mathematically derive in the context of relativity theory. In our models of physics, it becomes almost a mechanical fact. And essentially the reason is that the way it works is everything is represented by this network that corresponds to the structure of space, and sort of the things that happen to objects. Objects are represented by features of this network that represents the structure of space, and the sort of things that happen to objects correspond to sort of the rewriting of that network, the computational process that rewrites that network. And so one of the things one realizes is that when a thing is moving, how that works is the thing has to be sort of recreated at a different place in space. And that takes some computational effort to do. Similarly, the actual process of the thing going through time, so to speak, progressing through time, that takes some sort of computational effort to do as well. So the sort of mechanical picture is, if you're moving, you are spending some mechanical effort to recreate yourself at a different place as you move. And so then you have less computation left over to actually progress as yourself through time, so to speak. So that's kind of a mechanical reason that when things are moving faster, time progresses more slowly for them. So what does that mean in practice? Well, it means in practice, if you have an accurate clock that's in orbit around the Earth, that's going in low Earth orbit at 17,000 miles an hour or something, that clock will go a little bit slower than it would on the Earth. And that would be sort of obvious to observe if it weren't for the fact that, for example, on GPS satellites, the clocks are corrected for that effect, just to make it easier to receive GPS signals. But the clock, if left to its own devices, would be running a bit slower relative to a clock on the surface of the Earth. So in that leads to this thing called the twin paradox, which sort of says, well, if you're hanging out on the Earth, you have two twins, and one of them is hanging out on the Earth, and they live 100 years, let's say. Meanwhile, there's a twin who got zoomed off to go explore the stars, so to speak, and was in a spacecraft that succeeded in accelerating to 90% of the speed of light or something, and then turns around and comes back to Earth. And that twin who spent most of their time going at very high speed relative to the twin on Earth, that twin will have aged less than the twin on Earth because of this phenomenon of time passing more slowly if you're going faster. Well, it seems very weird, because why wouldn't you just say, well, to the twin who's in the spacecraft, it just looks like they to themselves look like they're standing still, but the twin on Earth is then moving relative to them. The sort of thing that unravels that sort of paradox is there's really a difference between the twin in the spacecraft and the twin on Earth. The twin in the spacecraft started from sort of the same being with the twin on Earth, but then in order to go off and zoom off at 90% of the speed of light or whatever, the twin in the spacecraft has to accelerate and then later on decelerate again. That acceleration is something that you can sense, you can detect. It's not something where it's sort of you don't notice whether you're accelerating or not. You do notice if you're accelerating. It's kind of the story of if you're in a plane or something, and it's going really fast, but to you it sort of feels just like you're standing still. Everything sort of works the same way in the plane, except if the plane is accelerating or decelerating, then you can tell, you're pushed back, you're pulled forward, whatever else. You can tell that there's acceleration. You can't tell for yourself unless you compare with something that's sort of going at a different speed. You can't tell just the presence of motion like that, of speed like that. So in any case, the end result is that sort of clocks run at different speeds in these different kind of in these different situations. In particular, there's a phenomenon called gravitational redshift that causes clocks to run more. I always have to think for a moment which way around this works. To run, let's see, when there's a gravitational field, the clock runs more slowly in a higher gravitational field. So that means, I'm making sure I'm getting this the right way around. It always takes me a moment to think about this. You can have I think one time I got myself very confused about this, and my memory has been confused ever since, and it requires that I actually work it out again to know how it works. But in any case, the point is the presence of a gravitational field affects just like this speed relative to some other clock affects it, so does being in a gravitational field. Well, that means that in principle, you can sort of mess around with the speed that things run at. You have a computer, it's running at a certain speed, you put it in a gravitational field. Relative to somebody who isn't in that gravitational field, it will run at a different speed. Just like if the thing is going fast relative to you, if you're at rest, it'll run at a different speed. So there are really funky things that happen, like in a black hole, where kind of you have the sort of most extreme distortion of space and time. You have a situation where if you're sort of falling into a black hole from the outside, it seems that you just sort of freeze right when you get to the event horizon of the black hole. You from the outside, it's kind of like time doesn't seem to be passing for you, but to you, you'll just sort of happily fall into the black hole without kind of noticing that's happening, except that if you look at the rest of the universe, during the time that you're falling into the black hole, the whole of the history of the rest of the universe will play itself out. So that means if you're doing things with computers, you can imagine that as someone falling into the black hole, you can say, well, I want this computation done. Let me see that being done in the rest of the universe. There's an infinite time for it to be done in the rest of the universe while you're kind of falling into the black hole and observing it. You don't get to control what's happening in the rest of the universe because you can't send a signal out from where you are. But if you're just observing what's happening, it's like you're observing sort of an infinite amount of computation happening. All these things are, in the end, when you unravel them, you discover that you sort of can't get something for nothing. And sort of when you unravel it, you find out that really the sort of the amount of computation you can get done is, well, with reasonable assumptions about what you're like as a doer of the computation or observer of the computation, you I think find out you sort of can't get further than you would in just without sort of the assist of gravity, so to speak. I mean, it's all rather confusing, and it's not even the idea of how black holes worked confused people for more than 50 years, because the mathematics of black holes means that at this event horizon where light can't escape from the black hole, the coordinates that represent what's going on have the singularity, they go to infinity. But that isn't really something that affects kind of, if you're falling into the black hole, nothing dramatic happens at the event horizon. Nothing really dramatic happens until you get to the center of the black hole where there's a singularity in the structure of space. Anyway, I think I've talked a bunch about black holes at other times here. They're always a bit complicated, and it's always a bit challenging to unravel the kind of the sort of the mathematical version of them, which is in some sense, once you understand that math is reasonably straightforward, with the sort of physical interpretation, which is sometimes not nearly as straightforward. And sometimes the mathematics is implicitly assuming things which are sort of not realizable in a physical way. Let's see. Gosh, lots of complicated things here. So Jason is asking, can we send a robot into a black hole and find out what's inside? No, because no with a footnote. The question is, how does the robot tell us what's going on? Well, the robot's going to send a radio signal. The problem is that there's so much force of gravity that that radio signal, the photons in that radio signal, get pulled back by the force of gravity and can never escape from the black hole. So the robot spacecraft will be transmitting all kinds of stuff from its radio antenna, but none of those radio signals will actually escape and get back to us. Now, there's a slight footnote to that, which is black holes eventually evaporate. What roughly happens is that, and this is a messy story, it's a story of sort of a mixture between thinking about things in terms of gravity and the structure of space-time and thinking about things in terms of particle physics and quantum fields and things like electrons that are constantly undergoing fluctuations, and there are vacuum fluctuations that are creating electron-positron pairs and all kinds of things like that. The qualitative picture of so-called Hawking radiation is that you have this event horizon, and all the time in the vacuum, there are virtual electron-positron pairs, let's say, being produced. And what can happen in sort of this mixture of mathematical pictures is that this pair of electron and positron get produced for a very short time, then they annihilate again. But while they have been produced, one of them can be pulled into the black hole behind the event horizon, so to speak. And that means the other one is on its own. It can't annihilate again. So what happens physically is that it gets emitted as radiation. It's kind of the black hole is kind of emitting radiation. Now, this is a bit of a complicated mess, right? Because I just explained that sort of all things fall into the black hole. Yet here's an example of something that isn't falling into the black hole. It's actually being radiated out from the black hole. But the reason that happens is this sort of mixture of these two very different descriptions of the world. In our models, there is a sort of a more elaborate version of this. But let's just say that when this radiation occurs of things sort of being, as a result of these quantum fluctuations, being sort of emitted from the black hole, eventually all the mass of the black hole is emitted in this radiation, and the black hole just stops being a black hole. It disappears. It actually does so quite violently because at the end, as the black hole gets smaller and smaller, there's a faster and faster rate of radiation. So that means that you might say, well, things that went into the black hole, somehow, in some sense, they'll come out. Well, not really, because the way that they'll come out is they'll be infinitely shredded inside the black hole. What comes out of the black hole is just pieces of these vacuum fluctuations. That spacecraft that went in, it was long ago, it was ground up into this, for example, the space-time singularity at the center of the black hole will take any physical object and kind of sort of crush it to something which is sort of no longer has any pieces hanging together, so to speak. The usual description of that in traditional general relativity is a mess, because in traditional general relativity, there's an equation that describes the curvature of space-time, and that equation is supposed to apply, well, everywhere in the universe. Except it turns out that when you have a black hole, the equation basically says, I don't apply at least one point in the black hole. The equation sort of says infinity equals infinity somewhere. And so the way that's often interpreted is to say, well, actually, in the sort of manifold of the universe, there's this hole punched out of it right at the center of a black hole. Right at the center of a black hole, the usual laws of the universe don't apply. That's the picture in sort of the traditional view of mathematical physics, view of gravity and space-time. In our models, the structure of space is just this network. And so this idea and what happens at this place where there's this singularity in space-time, what actually happens is, in a sense, much easier to describe. It's just this network is continually being updated. That's kind of the progress of time, is the updating of this network. But it turns out there can be situations in which this network just stops being updated. There are no more updates that apply. So in effect, time stops. And that's kind of, in our models, that's sort of all that happens, in a sense, in this at the center of a black hole. And so what would happen to the spacecraft that's falling in there? Well, the spacecraft will eventually just be frozen. It will be whatever configuration it was in. Nothing will ever progress. It will not. The sort of the spacecraft will, in a sense, not exist, because sort of from the outside, it's like nothing. There's nothing that later on sort of can come out of what's at the center of the black hole, because time has stopped there. So there's nothing can be a thing that is changing in time and moving, for example. Well, what happens at the horizon of a black hole in our models is something quite bizarre. See, one of the things that's always been mysterious is that in a black hole, stuff is falling into the black hole. And you could say, well, there's all sorts of things that are very precise quantum mechanical things that fall into the black hole. And somehow what comes out of the black hole is this mess that didn't maintain sort of the quantum precision, the pure quantum states that went into the black hole. How can this be? It seems sort of paradoxical. It's a consequence in the mathematical formalism of the fact you've mixed together the mathematics of gravity and the mathematics of quantum mechanics, which haven't traditionally fitted together very well. Well, in our models, things happen that are perhaps more bizarre. One of the things that happens is that there's a question. For example, when there's a vacuum fluctuation or something like it, did one of the electron or the positron from electron-positron pair, did that thing fall into the black hole? Did you see it fall in? Well, to see it fall in, you're this observer close to the event horizon of a black hole, already in a very exotic setting. But it turns out in our models, there's kind of a different kind of event horizon. We call it a branchial event horizon, and which is actually presumably outside the normal event horizon. And at that event horizon, something else really weird happens, which is that as an observer, you can't essentially form a classical thought. So in quantum mechanics, one of the big features of quantum mechanics is instead of sort of definite things happening in the world, there are many paths of history that can be followed. And normally in quantum mechanics, you just get to talk about the probabilities of what happens across all those paths. But when we kind of observe a quantum system, we find some way to knit together those paths of history and say, okay, we know a definite thing happened. Well, the problem is that it seems that an observer near a black hole will not be able to do that knitting. It will take an observer an infinite time to kind of knit together those threads of history that were produced by quantum mechanics. So in a sense, one could say the observer can't form a classical thought, can't form a definite decision about what happened. The observer close to a black hole will be sort of forced to be uncertain forever about what actually happened. Uncertain for long enough, they'll be uncertain until the black hole no longer exists, at which point the sort of all bets are off and that environment has changed. So it's kind of a resolution of what's a thing called the black hole information paradox, which seems to be quite nicely resolved in our models. But that's sort of the way that the main thing to realize is any sort of stuff that goes through being sort of sucked into a black hole and it comes out again, it's been sort of ground to nothing by the time it comes out. It no longer has any of the kind of features of what went in. So that spacecraft that went in to observe the black hole, it's every one of its atoms has been destroyed and turned into sort of elements of sort of ground up into what we call EAMs, these sort of atoms of space and so on. Let's see. Well, Brianna is asking more black hole questions. If you had an indestructible rope dangled into a black hole, could you pull it out again? Well, the problem is the rope will break. A rope is held together by the forces that hold atoms together. Those forces have a certain strength. The force of gravity associated with the black hole becomes infinitely large. And so any rope that is held together by the forces that hold atoms together will break. There's a similar kind of issue that comes up, which is the following thing. Imagine that you have a rod and you're twirling the rod around at the center, and the rod's really long. Well, eventually, the outer boundary, the outer part of the rod will be going faster than the speed of light. If you just calculated, I'm turning the rod around here at a certain speed, by the time I'm out at the orbit of Jupiter or something, the tip of the rod will be going faster than the speed of light. Well, why doesn't that work? Well, the reason it doesn't work is that as you try and make it go that fast, you need to put more and more and more force to make it go faster and faster and faster. And eventually, it is inevitable that the rod made of any material will break. In other words, the internal forces necessary to keep it as a solid object can never withstand the forces that you need to put in to get that tip to go at the speed of light, for example. So, and that's a typical way that a lot of these kind of paradoxes about sort of the interaction of gravity and relativity and so on with kind of everyday experience, that's a lot of how they get resolved. I mean, I have to say, when people talk about relativity and they give these examples of kind of fast cars going through barns and closing doors, and the car is foreshortened and can close both the doors and so on, almost all of those things make sort of implicit assumptions about the possibility of, for example, solid objects that do things that sort of solid objects held together by atomic forces just can't do. That's a fairly typical way that those paradoxes kind of get themselves messed up. I mean, there's another one that I guess I was responsible for a long time ago that has to do with vacuum fluctuations. So as I mentioned, one feature of, you might think in the vacuum, there's just nothing there. Well, that's not true at all. In our models, what's there is all of this detailed network that forms space. Without that detailed network and without the activity in that detailed network, you just wouldn't have the extent of space. You wouldn't have a thing where you can say you have to travel from one side to the other. So in our models, there's something very sort of explicit that's there in the structure of space. And by the way, sort of what maintains the structure of space is the continued activity of this network. The fact that there's an event that rewrites this little piece of network that affects an event that rewrites another piece of network and so on. That continual sort of interaction of those events is what maintains the structure of space. It's a little bit like what happens, I don't know, in a gas like air, for example. If you put air in a box and you try and sort of compress the box, what's sort of maintaining the structure of the air is the fact that all the molecules are colliding with each other. It's this continual interaction that's maintaining the structure of this thing that we consider in that case to be some gas in our box. In our models, what maintains the structure of space is this kind of continued interaction between the atoms of space, these ems that correspond to the sort of atoms of existence in our universe. Well, that's the version in our models. And if you kind of zoom out from that, you can say, well, there's this sort of all this bubbling around that's happening in the structure of space. How do we interpret that? We can interpret that in terms of kind of virtual particles. So, and that interpretation kind of corresponds to what one talks about in traditional last 100 years or so, quantum mechanics, quantum field theory, and so on. So in that case, what happens in the vacuum in quantum field theory is the following thing. So there are ordinary particles like electrons, and there are antiparticles, positrons, and so on. And the electron has a certain mass, about 500,000 electron volts or whatever. And that's what an electron, a free electron that's just sort of trundling around, has that mass. But one feature of quantum mechanics is that if you that for very short periods of time, the usual kind of rules about what particles can exist and so on no longer work. That's a consequence of the uncertainty principle. But maybe a better way to explain it is to say that just as, well, okay, so if you're trying to, for example, measure both the position and the momentum of a particle, the energy and a time, those things, you can't ever sort of measure them precisely at the same time. Let me explain that. So the uncertainty principle, probably easiest for position and momentum. So let's talk about something where the kind of the density of the thing corresponds to a wave. And let's say that you want to measure, it corresponds to something which kind of wiggles. Okay, let's say you've got the position of a thing, and you say, okay, I'm going to describe the probability to find the thing at a particular position, and it's some function as a function of position, and that function wiggles around a bit and it has a big maximum and then gets smaller. Okay, the position of that big maximum, you'd say, well, that's where the thing is likely to be because that's where there's all the probability of it being. Well, it turns out in quantum mechanics, the rate of wiggling of that probability as a function of position turns out to correspond to the momentum of the thing. So Schrodinger's equation kind of relates tells you how that probability distribution works, and it tells you kind of the sort of based on that, you end up discovering that it's the kind of rate of wiggling that tells you the momentum, and it's the kind of the overall value that tells you the position. So you can have this thing that wiggles around a bit and has a big maximum, then wiggles around a bit. You can say, well, I know where that thing is because it has that big maximum in that place. But the momentum it's a thing that depends on sort of the rate of wiggling, the wavelength of the wiggles. But because you didn't get very many wiggles, you just got this one big maximum, then you can't really say very well what the rate of wiggling is because you just didn't see very many wiggles. So if you can localize the position very well, you can't localize the momentum. You don't have sort of enough wiggles to know really what the momentum is. On the other hand, if it's just sort of all wiggles and there's no big maximum anywhere, you can absolutely localize the momentum. You can figure out the frequency of the wiggles and so on. You get that very accurate, but you don't kind of know, you can't localize the position. So that leads to this kind of uncertainty relation that the uncertainty in the position multiplied by the uncertainty in momentum is larger than some value. That's a sort of typical result. That result in the case of sort of wiggles and so on, waves, that's just a result about the mathematics of waves and about Fourier analysis and so on. But when that's interpreted, when those waves are interpreted as probabilities of particles, then you have, through quantum mechanics, you have this uncertainty principle. And the uncertainty principle says you can't simultaneously localize kind of the position and the momentum, or the energy and the time. And those are that's sort of a fundamental feature of quantum mechanics. If you allow yourself only a limited time to make a measurement, you will be quite uncertain about the energy, and so on. Okay, so in quantum mechanics, there's another sort of uncertainty principle, which is actually the number of particles that are present. So if you've got something that can have one photon, two photons, three photons, one electron, two electrons, whatever, the way that quantum mechanics works, there is always uncertainty in the number of particles. So there is always some sense in which you don't know for sure just how many particles there were. So sort of physically, the way that shows up is even in the vacuum in quantum field theory, there are an infinite collection of fluctuations where you'll get these kind of electron-positron pairs that get produced and then destroyed after very short amounts of time. It's kind of also related to that energy-time uncertainty relation, because if there's a short enough time, then you can be uncertain enough about the energy that there could be enough energy to produce an electron and a positron with their masses. There could be enough energy, you just wouldn't notice because the amount of time that happens for is too short. So sort of the picture of the vacuum in quantum field theory is this whole collection of every possible sort of mode of every field which corresponds to a particle is present in some amount. So to say it a little bit more mathily, the way that in quantum field theory, okay, it's a little complicated. In quantum field theory, you might say, oh, quantum field theory describes things like electrons and so on. It doesn't really quite do that. Quantum field theory says you can have something that corresponds to an electron coming in from the infinite distance. Eventually, it's going to interact somewhere and it's going to go out an infinite distance as it goes out. When the electron is sort of an infinite distance away, it behaves like a plane wave. It's kind of like it has a certain momentum, and that corresponds to a certain frequency of wiggles, and it's just a big sort of there's no all that's there is this kind of this field that is sort of that is wiggling at a certain frequency, and that's kind of the way that the sort of slightly idealized way that particles are represented in quantum field theory. Well, you can have an electron with any momentum. All different momenta are possible. So the way you represent that possibility in quantum field theory is to say there are all these modes of the field that correspond to all these different possible momenta for an electron, a photon, whatever else. And because of this uncertainty principle about number of particles, every one of those modes is present at some level. There's so a little bit more formally, the energy of a particle associated with a mode is you have sort of one particle associated with a mode, 2 particles, 3 particles, 4 particles, and each one of those, there's h bar, Planck's constant over pi, it's sort of fundamental constant of quantum mechanics, and omega, the angular frequency of the particle. Actually, I could say it differently. It's Planck's constant h multiplied by the frequency of this sort of wiggling that corresponds to the momentum of the particle. So it's Planck's constant times the frequency gives you energy of a mode of this field. Well, you can have in each mode, you can either have 1 particle present, 2 particles, 3 particles, or whatever, but you don't get to 0 particles. The lowest you ever get is a half the Planck's constant times the frequency. So there's always some 0 energy, zero fluctuation in every mode of a quantum field. It's kind of a weird thing. I have to say, I think it has a pretty clear interpretation in our models in terms of the fact that sort of in the structure of space, there is sort of continual activity everywhere in the structure of space, sort of at all scales. If you want to represent that by saying, well, all this activity corresponds to something like these plane wave type things that correspond to particles, you'll end up with sort of all those possible plane waves being things that you can decompose the things that are actually happening in the structure of space into. Okay, so everywhere in traditional quantum field theory, everywhere in space, there are these vacuum fluctuations where particles are being created and destroyed in very short amounts of time, and that's a sort of an effect. Well, so there's a phenomenon called the Casimir effect, which is sort of an interesting version of a sort of measurable consequence of all these vacuum fluctuations, and it works like this. Let's say you have 2 plates, metal plates, and you've got vacuum in between them. Well, turns out that the vacuum in between these modes of these fields, you can only have, again, we're talking about these sort of wiggles that represent the momentum, energy associated with these fields. When you have these plates there, sort of the plates sort of force these wiggles to have value 0 at each plate. So you can kind of fit, it's like a string where you can have a certain fundamental frequency that corresponds to the string sort of bowing out once in between 2 attachment points. You can have a higher frequency where it bows out twice between those attachment points and so on. But you can't have a lower frequency because then those 2 attachment points the string has to be attached at those points, a sort of a slower bowing of the string. It wouldn't get to 0 at those 2 ends. And it's sort of the same with quantum fields, that you get only down to a certain frequency of quantum field can sort of fit within these plates. A lower frequency of quantum field will sort of not be fitted between those plates. Okay, but outside of the plates, there's no such constraint. You can have arbitrarily low frequencies of quantum fields. And so then what you have is a situation where there's sort of lots of possible vacuum fluctuations of quantum field outside the plates, but there's only a limited connection of vacuum fluctuations in the quantum field between the plates. And so, needless to say, one might think there's some kind of force, because there's all these vacuum fluctuations on the outside that are sort of exerting a force on these plates, but there are fewer vacuum fluctuations on the inside. So the plates are kind of pushed together by having all these vacuum fluctuations on the outside. Well, that's a good picture. It's something that's been observed. It's a experimentally measured thing. That intuitive argument isn't in the end quite right. Because, for example, if you make a box, just a completely enclosed cuboidal box, then it turns out that it's no longer the case that the forces are kind of always pushing in on the box. For rather bizarre, I mean, when you work out the mathematics, you can have forces that push in and forces that push out. And something that I wrote back at the beginning of the 1980s, somebody noticed that if you looked at these different shapes of boxes, you could kind of make this closed cycle where you keep changing the shape of the box, and you could continually extract energy from the vacuum. By just changing the shape of the box, you kind of you take energy out because the forces work that way, and you can keep, you can make this closed cycle where you keep reshaping the box, and you're continually harvesting energy from the vacuum. Very bizarre kind of thing to imagine that would be possible, that you can get essentially a sort of first kind perpetual motion machine where energy is just suddenly appearing from the vacuum. Well, can that work? Well, the answer is no, not in practice, because the way that has to work, it has to be the case that the walls of the box are never transparent to any frequency of radiation, however large. And much like the kind of rod that breaks when you have to have its tip go at the speed of light, in the end, when you have a thick made of metal or something like this, that the metal does great at preventing radio waves from going through and things like that. But by the time you have high enough energy, high enough frequency waves like X-rays or gamma rays or something like that, eventually you'll punch through. The atomic forces will not be strong enough to prevent kind of the effect of that quantum field, wave, whatever, from getting through. So it's again one of these effects where when you have realistic or even semi-realistic kind of materials, the effect doesn't, you can't do this thing of sort of harvesting energy from the vacuum. What will end up happening is that the vacuum kind of, the energy you thought you were harvesting kind of leaks out through the walls of this box. Let's see. Oh boy, there's all kinds of questions here. Eggy is asking, you look for explanations about ions. They're usually explained in terms of electron shells. Is there a more fundamental way to explain the existence of ions? Okay, you guys are asking a whole bunch of physics questions here. And these are quite hard, It's even given, I mean, I'm trying to in real time translate between sort of mathematical physics versions of these things that are full of sort of formalism and sort of my attempt at intuitive explanations that kind of still sort of accurately reflect what's fundamentally going on. Okay, let's talk about atoms for a second. So what's in an atom? There's a nucleus made of protons and neutrons. It's pretty small. Then around the nucleus, there are a bunch of electrons hanging around. And the way an atom normally works is there's a positive electric charge associated with the protons in the nucleus. The electrons have a negative electric charge. Unlike charges attract, so the protons pull in the electrons, and you get something where the atom is sort of pulled together by the electric forces pulling the electrons towards the protons. Now, an interesting question would be, how come the atom doesn't just collapse? How come the electron doesn't just spiral into the nucleus and go splat? I mean, after all, there's a force of attraction. And if it was like gravity, for example, you just have something spiraling in, and eventually it loses energy, and it can spiral in, and then just sort of go splat on the surface of the planet or whatever it is. So why don't electrons just spiral in and and sort of hit the protons in the middle, so to speak? Well, the answer is a fundamental phenomenon of quantum mechanics, actually related to the things I was just talking about the uncertainty principle and so on. Um, it is a, how to explain this from first principles? Well, it is a fact of quantum mechanics that you, okay, let's explain it this way. If we think about sort of the probability for an electron to be somewhere being represented by something that's a kind of a wiggling wave. Well, it turns out that there is always a sort of, if you are going to have that sort of wiggling wave fit around the nucleus, there's always sort of a minimum number, a minimum amount of wiggling that must be there. That's a very vague way of saying the fundamental fact about quantum mechanics, which is that the energy levels in the system are quantized. It has to be the case that the energy of the electron is it comes in discrete jumps, and that's sort of a fundamental feature of quantum mechanics. Let's see, in terms of can we explain? I mean, let's just say one hasn't known any more fundamental statement than that. It is a fact about quantum mechanics that energy is quantized, that if you keep the electron within this kind of limited size region, it necessarily has to have an energy that is not precisely zero. And in order for it to kind of in order for it to kind of go and collide with it, sort of spiral in and hit the nucleus and so on, it would end up having to it wouldn't be able to maintain the energy that it has to have according to quantum mechanics by being constrained in a box of a certain size. Now the question is there a, I can explain that you solve the Schrodinger equation. It's the equation that describes the so-called quantum amplitude, roughly the probability to find an electron in a particular place. That equation has a particular form, and when you try and solve that equation for an electron in an atom where the electron is going to have sort of the same configuration forever in the atom, that when you solve the Schrodinger equation, you find out that it's an equation that looks very much like the equations that you get when you have a string with two attachment points or something, and you're asking what are the possible modes of the string. It's the same kind of equation, and it's for the same reason as the fact that there's a discrete set of modes in the string, that there are a discrete set of modes for the electron. Now, is there a way to understand that sort of at a more fundamental level using our model of physics? I think the answer is yes, but I mean, eventually the answer should better be yes. I think about this for a second. Yeah, I mean, I think, gosh, is there an easy way to explain this? Probably not right now. Hopefully we will get an easy way to explain that in time. I mean, I think, yes, no, I think it's sort of, it's kind of my intuitive understanding of it is still sufficiently fuzzy and involves sufficiently many abstract concepts that I think it's not, I won't succeed in trying to explain it right now. But in any case, the fact of quantum mechanics is that there is a distinct set of energy levels that an electron confined inside an atom has to have. And those are in the language of quantum mechanics, those are the so-called principal quantum numbers associated with an electron, usually denoted n, for the principal quantum number, and it can be value 1, 2, 3, 4, 5, etc. And actually, it usually starts at 0, but that doesn't correspond to, that still corresponds to the electron is kind of being held outside the nucleus at some definite radius. It's in the case of a single proton, it's the so-called Bohr radius. It's about 1/10 billionth of a meter, whereas in scientific notation, it's 10 to the minus 10 meters, whereas the size of the nucleus is about 10 to the minus 15 meters. So it's about 100,000 times smaller than the kind of average distance that the electron is held out from the nucleus. So, okay, that's what that's sort of the ground state. The lowest energy is the electron sort of being held out of the nucleus at that average distance. If you put more energy into the system, the electron will gradually be sort of further and further away from the nucleus and have more energy. It'll have 1 unit, 2 units, 3 units, 4 units of energy, and so on. Well, actually, as you put more and more energy into the electron, it will sort of get a little bit further away from the nucleus, but actually its energy, its energy levels get closer and closer together as you sort of this quantum number, as you increase the quantum number, the energy levels get closer together until eventually the energy levels are such that the electron will escape from the nucleus. Eventually, it gets enough energy that it can tear itself away from the electric forces that pull it into the nucleus. And in the case of hydrogen atom, it's 13.6 electron volts is the energy you need to put in to ionize the atom, which means that the electron is no longer sort of held in place. One often talks about electron orbitals. There isn't really an orbit going on of the electron whizzing around the nucleus. That's not really the right picture. There's sort of an electron cloud that in some sense where sort of a cloud of where the electron could be, and that cloud is, if you put too much energy in, that cloud sort of has to dissipate and the electron will be free, independent of the nucleus. And that's when the thing becomes an ion. If you have a hydrogen atom, you have a proton and an electron in the hydrogen atom, in the simplest kind of hydrogen atom, and that if you make the electron have enough energy, the electron will escape from the nucleus and be freely floating around doing whatever electrons do. And then you say that the thing that's left behind, just the raw proton, is an ion, a hydrogen ion. And for example, if you're doing chemistry and you have pH levels are the logarithmic amount of hydrogen ions that exist, sort of hydrogen atoms where they've been ionized, so it's just a proton separated from an electron. Okay, so that's roughly what happens. In a hydrogen atom, atoms of other elements, helium, lithium, beryllium, and so on, each successive element has more protons in its nucleus, has more positive electric charge in its nucleus, needs more electrons to neutralize that charge, so you have a neutral atom. So it has more electrons kind of around the nucleus. Helium has 2, lithium has 3, and so on. Carbon has 6, et cetera, et cetera, et cetera. That's the atomic number, which gives the position in the periodic table of the element. So when you talk about sort of ionization of, I don't know, let's say oxygen, which is 8, when you say it's getting ionized, what you mean is that of the 8 electrons that would usually be there, some of those electrons have too high an energy and they've escaped. And so what's left is this thing with an unequal number of electrons and protons. It has an electric charge that has all sorts of consequences, but that's the ion is the thing that is left over when some of the electrons are pulled away. You can also have ions where there are extra electrons that have been sort of stuffed in, and then again they have that has a net electric charge. The whole question of sort of how do you put energy into electrons to ionize an atom? Well, you can use photons. You can sort of shine light on the atom, and the electron will absorb that light. The light comes in the form of a photon. The electron absorbs that photon. The photon has a certain amount of energy. The energy that was in the photon causes the electron to change its energy state, go into a different energy state. So in the case of hydrogen, with a single nucleus of a proton and electron, it turns out if you have ultraviolet light, a certain that's the kind of the photons in ultraviolet light have higher energy than the photons in visible light. The energy in ultraviolet light is sufficient to feed in that 13.6 electron volts that will cause the electron that was originally in the ground state, in the lowest energy state in a hydrogen atom. It will give it enough energy that it can escape from the proton, and it will ionize the hydrogen atom. So that's a way to ionize the hydrogen atom. Now, by the way, sort of a famous time when ionization of hydrogen atoms stopped was about 100,000 years after the Big Bang, at the beginning of the universe. When there's enough sort of energy around, enough photons with high energy and so on, then hydrogen atoms can't survive. So in the very early stages of the Big Bang, no hydrogen atom with a proton and an electron bound together just wouldn't survive. They if they formed for a very short time, they get torn apart again by the fact that there are all these photons bouncing around and other things that can transfer energy to the electron, pull it out of the atom. Well, as the universe got bigger, it effectively cooled down, and at some moment, I think about 100,000 years after the beginning of the universe, the typical energy of photons in the universe went below that 13.6 electron volts. So it was no longer, so those photons were no longer to the point where they could ionize hydrogen. And so that meant that hydrogen atoms, ordinary neutral hydrogen atoms, could form. Why is that important? Well, ionized hydrogen, for example, with those free electrons and so on, it absorbs photons. So photons that are going around, they'll keep interacting with those electrons that are there. Once you have a neutral atom, it has much less interaction with a photon, with electromagnetic radiation, with electric fields, whatever else. It's the neutral atom it has sufficiently little interaction that a hydrogen gas, for example, is transparent. You put to visible light, for example, you can put, or to electromagnetic radiation, well, let's say just visible light. But those neutral atoms don't, they don't as dramatically absorb photons as free electrons do. So that means that in the early universe, at the moment of recombination, as it's called, I don't know why it's called recombination, because actually the electrons and protons weren't combined before. This is the first time in the history of the universe that they got combined, but it's usually called recombination. This moment where it starts to be the case that actual neutral hydrogen atoms can form, and the thing that was this ionized gas, a so-called plasma, that's what an ionized gas, it's the name for an ionized gas. The plasma would have stopped photons, and so any photons that existed earlier than that, you don't get to kind of they don't get to reach us because they were absorbed by some ion, some electron that existed, 50,000 years after the beginning of the universe, long gone. But at that moment it's not one moment actually, it's over a sort of period of time, around 100,000 years after the beginning of the universe, where the electrons and protons combined into atoms, and the universe became transparent to light. And so that means that sort of light that originated at that time has been just trundling towards us, going through kind of space that is now transparent to that kind of light. And that the light that originated at that time is precisely the cosmic microwave background. Because of the expansion of the universe, what started as ultraviolet light has ended up now being microwaves at much lower frequency, just because of the expansion of the universe and the Doppler effect and all those kinds of things. But anyway, I think so the idea of ions, it's always about atoms that don't have their sort of standard complement of electrons, too few, too many, and so on. And well, there's a whole lot that one can say about chemistry to do with sort of the these ions and electronegativity and kind of the amount that an ion can sort of pull on other electrons and so on. I mean, a big story of chemistry is that when you put two atoms near each other, these sort of electron clouds one could talk about between those two atoms sort of start interacting with each other. And they can interact in a whole variety of ways. They can do things like they can start exchanging electrons from between different atoms. That's something that leads to sort of bonding of two atoms as they keep on exchanging electrons. Then there are a whole bunch of other effects. Actually, I'll mention one effect that sort of relates to a thing I was talking about before, which is so-called van der Waals forces, which are kind of the weak forces that hold that between molecules. So, or between atoms, actually. Neutral atoms, you just got, you know, a hydrogen atom here, a hydrogen atom there. They're just hanging out. They have no electric charge. Why should they have any force of attraction between them or any force between them? Well, they have a tiny force of attraction because they both have mass. So there'll be an absolutely tiny, tiny force of gravity between them. But there's another force as well, so-called van der Waals force. And it has a rather weird origin. And essentially the origin is this. An ordinary neutral hydrogen atom is in its ground state, basically has a symmetric distribution of charge. It's like it's a sort of a sphere. The electron cloud is kind of just like a simple sphere. Okay, but remember those vacuum fluctuations I mentioned earlier, that everywhere in the vacuum, there's a certain rate of sort of little pieces of energy that come into existence and then disappear. Well, those vacuum fluctuations can affect a hydrogen atom. And what they will do is, instead of it being a nice spherical hydrogen atom, they'll keep kicking it and it'll keep on it'll get distorted. For just a tiny moment, it'll get distorted. It'll be elongated, for example. So there'll be part of instead of it being the case that the electron sort of cancels the charge of the proton everywhere, the proton will get sort of, just for a moment, as a result of vacuum fluctuations, will get pulled a little bit apart. Okay, well, that creates, so there's a little plus charge, a little minus charge, a little bit distance apart as a result of vacuum fluctuations for a tiny amount of time. Okay, well, when you have a so-called electric dipole, okay, I should explain something. When you have the force of attraction between things electrically has an inverse square law, just like the law of gravity, actually. It means that the force associated with of attraction between one electric charge and another electric charge decreases like 1 over r squared, where r is the distance between them. It's actually pretty easy to see why that's the case, because essentially what happens when you have an electric charge, that produces electric field lines that kind of go out in a kind of idealized sort of hedgehog from that central charge. They're just all streaming out in different directions. Okay, so if you ask, well, if you have something which is another electric charge, for example, every time there's an electric field line, that electric field line can produce a force on that other charge. But what force does it produce? Well, the more electric field lines that sort of attach to the other charge, the more force there'll be on it. But how many electric field lines will there be? Well, we've got this thing that's sort of this idealized hedgehog with all these things pointing outwards, we can say, well, at any given, if that other charge is a certain size, at any given distance, we can ask sort of how those electric field lines will become more and more dilute, because there's a fixed number of those electric field lines that are covering a larger and larger area of sphere as we look further and further out from that central charge. And the area of a surface of a sphere is 4 pi r squared. That's just the formula for the radius of a sphere of radius r. The area of the surface is 4 pi r squared. So that means that if we ask, well, what's the sort of, how does the density of those electric field lines go down? Well, it goes down as the area increases, the density goes down like 1 over r squared. And that's basically why the force of attraction of two electric charges decreases like 1 over r squared. Okay, well, turns out if you work out the math, if you have a positive charge and a negative charge, if they were right on top of each other, they just cancel out and there'd be zero force. But if they're a little distance apart, there is actually a force, but it's no longer 1 over r squared, it's 1 over r cubed force law. And the distance between the charges is let's say a. I guess the force is proportional to a over r cubed. So as a goes to zero, it just goes to zero. But there's a small force associated with this dipole that falls off more quickly than the force associated with a single charge, but it's still something that's there. Okay, so we've got our atom. Our atom keeps on getting kicked by these vacuum fluctuations. For a brief moment, it acts as a dipole. So that means it exerts a force on something else. And that force, okay, so then there's another atom, let's say. That force on the other atom actually will elongate that other atom and will make it have sort of a form of a dipole. It will separate the proton and the electron. It's just the way that the force law works for dipoles. It's such that it will pull those things apart just a little bit. So vacuum fluctuations, one side on the atom, produce this sort of tiny dipole for a brief time. That tiny dipole then induces a tiny dipole in this other atom that's over here. And then the result of that is that other dipole then interacts with the first dipole. Bottom line, there is a force of attraction between those two atoms as a result of vacuum fluctuations producing a dipole here that induces a dipole here that then acts back on the dipole there, and there's a force of attraction. And it turns out, because the force law for dipoles is 1 over r cubed, and there are sort of two levels of dipoles affecting dipoles, the force law is 1 over r to the 6th. So the van der Waals force law between neutral atoms goes down roughly 1 over r to the 6th. Now it's a little trickier than that, as always. And in fact, it's more like 1 over r to the 7th, because it turns out there's an additional piece of trickiness, which is there's sort of the effect of one dipole on the other has, it only can affect the other dipole at the speed of light. And when you factor that in, that produces 1 over r to the 7th. So that means between neutral atoms, there tends to be this force of attraction, let's about 1 over r to the 6th. And if you work out when people try to work out kind of the sort of when they're doing calculations about how solids work and so on, it's very common to have a thing called the Lennard-Jones potential, which has a sort of force of attraction that's 1 over r to the 6th. And then when the atoms get too close together, they start repelling each other, different set of effects. That's a different set of effects associated with mostly exclusion principle for electrons. And then there's a 1 over r to the 12th that comes in. So it's sort of plus 1 over r to the 6th minus 1 over r to the 12th. And that's kind of the thing that makes a solid work the way it does, is there's these forces of attraction and then forces of repulsion between atoms. Actually, no, not a solid. I should have said in something like a gas. That's in a solid there are different forces that come into play. For example, there are something like ionic crystals, like salt, sodium chloride, has some that works by the fact that let me not go into that. That's a different rabbit hole. But in any case, that's just a little bit of a story about atoms and ions and forces of attraction between them and such like. I think it's time for me to go back to my day job where I actually have to work on something to do with chemistry. Well, thanks for asking. There's a lot of physics questions today. I feel it's, as I say, it's a bit challenging sometimes with these physics questions because the way that physics has evolved in the last century or so has been very mathematical. And a lot of these things, there's a clear mathematical way to say, oh, we've got the Schrodinger equation, it's, del squared psi, I d by dt psi equals, h bar over et cetera, et cetera, et cetera. It's, you can say these equations and things, but it isn't very useful for understanding what's going on. And usually the best that one has been able to get in physics is sort of the equation-based understanding of what's going on. And sort of these more mechanical explanations of what's going on are something that is kind of a thing that comes after the fact once you've seen sort of how the math worked out. At least that's been the traditional story in physics. In our model of fundamental physics, one is actually able to get a little bit back to something that is a more mechanical set of explanations. Although that when one says mechanical, one's dealing with that the sort of fundamental ingredients are at absolutely tiny scales, and there's sort of a huge amount of sort of irreducible computation between what happens at those small scales and what happens at the scales that we experience. And so there are a different set of sort of intuitive jumps that are needed to go from that very small scale to the scale that we're dealing with. But I think in many cases, it becomes a more mechanically intuitive explanation of what's happening. And things like why is there a lowest energy level for an electron in an atom? I actually thought about that a few years ago, and I think, again, as I say, I have sort of an intuitive picture of how that works in our models, but it could probably be made a lot more mechanical and perhaps explainable in a way without any mathematics or anything like that. But we're not quite there yet. But in any case, this was kind of a more sort of a window into the sort of attempt to put an intuitive overlay over kind of the mathematics of kind of 20th century mathematical physics. All right. Well, thanks for joining me, and I look forward to chatting with you again soon. As I say, it's the beginning of our annual collection of summer programs, our summer school for grown-ups and our summer research program for high school students. And I think I will try to do a few of these live streams in the middle of those summer programs, actually with a live audience, which is fun for me. Next few weeks, it's a bit challenging because one of the features of our summer programs is that sort of the goal is for everybody to do an original project, and the question is, where do those projects come from? How does one get topics for those projects? Well, in the end, for almost all of them, I make them up. And so in the next week or two, I get to figure out projects for, well, let's see, about 70 people for our summer school, another 70, 80 people for our high school program. So that's a lot of projects to figure out. I think the typical kind of professor who has graduate students maybe has to figure out one project a year. I'm trying to do sort of hyper professoring at the rate of 150 projects per year or something. But that's so I'll be a bit busy doing that along with some aspects of my day job, so to speak, in the next week or so. But I hope I'll have a chance to do some more of these live streams before too long, and look forward to that. Thanks for joining me. Bye for now.